Hi everyone! I'll start with a brief introduction. For those who see me for the first time, I'm Anna, Flutter and Dart GDE from Ukraine. I am also a Women Tech Makers ambassador and a Flutterista. I'm passionate about quality software and spreading the knowledge I gained with over a decade of experience in cross-platform mobile apps development. I regularly talk at tech conferences and write deep dive technical articles about Flutter. So if you're interested in deepening your knowledge in this area, make sure to subscribe to my social accounts. Speaking of that, let's check my YouTube. About 2 years ago, I gave my first big conference talk, Code Less, Deliver More, at the first Flutteristas conference, where I spoke about using build runner and code generating packages when solving typical tasks in mobile app development. Even though sometimes code generation is considered a controversial topic, for me it became an integral part of my everyday development experience. I became so passionate about the topic that about a year ago I spoke about it again in Fun with Code Generation session at the Flutter Vikings conference in Oslo, providing even more examples of how code generation can simplify developer lives. I'd like to stop at this slide in particular. This is a list of packages used in most of Flutter projects I work on. It already facilitates a lot of daily tasks like implementing JSON serialization and REST API communication, navigation and localization, dependency injection tests. So these examples inspired me to look for more opportunities for optimization with code generation. And here is the one I came up with. If you are working on a project of any significant size, it's quite likely that you have chosen to split the functionality between multiple packages. Inside those packages, some of the code should be available for usage from other packages, and some code should remain inaccessible for encapsulating the implementation details. The same is applicable if you are working on a package that you want to publish on pub.dev. You only want to expose the public API of the package while hiding all the unnecessary details, so its users won't be distracted and the package won't be misused. For that, you place all of your code under the libsrc folder and control its visibility from the file under the lib folder that contains a bunch of export directives. These files are called index or barrel files. They are typically named after the package name, although you can have more than one such file under the lib folder. So here is what I find slightly uncomfortable and where I see the opportunity for optimization. Developers have to compose these files manually, have to remember to update them in case the code visibility has to change, and have to check those files to see if the code is going to be public. You see, for making some code private inside a single Dart file or a library, it's enough to name them with an underscore at the beginning. And as a result, you immediately control code visibility while developing. And it's also very easy to understand its visibility while reading the code later. But to control the code visibility on a package scale, you write the code in one Dart file and then control its visibility to external users in another. So today in this session, Code Less, Deliver Even More, I'm determined to change this and develop a code generating package that will allow to annotate the code that should be accessible from outside the package with a special annotation right above that code. and then we'll generate a similar barrel file based on those annotations. Let me actually show you. Here is an example of what I mean. Every top element of the Dart file can be annotated with a special annotation, including barrel file. Here I'm showing a few examples like annotating a class, a global constant, and so on. In this file, I show that unannotated elements like this example class 2 and an unnamed extension won't be exposed. Also, pay attention that example class 1 is declared after example class 3. This is a file with no annotated elements. And finally, this is the example of a Dart library consisting of two part files where only part file contains annotated example class 2. And here is a file I want to be generated after I run my tool. We see that all elements from the example1 file are listed after show directive. For the second example, only class 1 and class 3 are exposed, and they are sorted alphabetically. There is no mention of example3 file as it did not contain any annotated elements. And finally, class 2 is correctly exposed from the example4 file, even though it was declared in the example4 part file. So this expected example file, I created it manually. And today we are going to see how to develop such a package that will generate a file exactly like this one. It may seem like an easy task, however, it's not that straightforward. So I'll show a couple of interesting cases and also will demonstrate what challenges you may face while developing your code-generating packages and how to solve them. Before we jump right into coding, let's seek some inspiration from other code generation packages to see how they solved their challenges and what's possible. Here is a demo project from my talk at Flutter Vikings. It is using all of those code generating packages in the list I showed before, and I'll use it to explain how some of them work. Let's check Freest first. To make and generate some code, we have to apply a special Freest annotation over a class and declare a future part file with the freest.dart extension. After the build runner executes, the new Dart file is created and it is a part of the original file. Let's dive into the source code. There is a Freest annotation package that contains a Freest annotation declaration and Freest package, which actually performs the code generation. We see that under the hood it uses a part builder from the source-scan package. The documentation says it is a builder that generates part of files, and file with specified .freest.dart extension will be created for each .dart input. Okay, interesting. We just learned that Freest consists of two packages and that it uses source-scan package and a part builder that will generate a part output file with custom extension for each input Dart file. Let's remember that. And let's take a look at JSON serializable now. Here it is used implicitly through Freest, but it doesn't change much. Same as with Freest, we have to declare a part.g.dart file and have it generated for each input Dart file that uses JSON serializable. Let's check the sources. We also see two packages. JSON annotation contains annotations, declarations, and some utilities, and JSON serializable is responsible for generating code. Let's see. In its builder, under the hood, it uses shared part builder, also from SourceGAN package. This builder also generates part of files, and it actually allows multiple code builders to write to a single .g.dart file. Let me demonstrate what I mean. Here is the usage of another code generating package, Retrofit. It also generated a .g.dart file for each .dart file that contains classes annotated with REST API annotation. And under the hood, well, first of all, it also consists of two packages. Retrofit package is a container for annotations and public APIs, and Retrofit generator contains a builder that uses shared part builder, same as JSON Serializable does. So, if this file here contained both Retrofit class and JSON Serializable class, both of those packages would be able to successfully generate their code in a single .g.dart file without overriding each other's outputs. So far we see certain patterns, right? First of all is to have two packages, one for annotations and one for the generator. That's because we don't want the generator to be among our project dependencies. It is supposed to generate the production code for us, but itself, it should go to dev dependencies. The annotations package, on the other hand, should be a direct dependency for our project because we annotate production code with them. And another pattern we see is that builders offered by the SourceGAN package assume there is a one-to-one match between a source Dart file and an output part file. For our scenario, we expect to have a single file output per package. So this is not exactly the way to go, although I will partially use this approach. Let's check another example, the injectable. See this annotation here. The way injectable works, it allows you to put annotations across the project in different files, and then gets them all together in a file next to this one thanks to this injectable init annotation. This sounds more similar to what I'm trying to achieve in my package. So let's see how they did it. Once again, two packages. In this case, injectable contains annotations, and injectable generator has a builder to generate code. Let's check that one. You see, here they have not one builder, as we saw previously, but two. Both of them return a library builder. It's a third type of builder provided by SourceGAN, and this one creates standalone Dart libraries. Simply put, self-sufficient Dart files without parts. So, why two builders? The top one will accept all Dart files of the package and will generate temporary .injectable.json files for each Dart file it has an injectable annotation. And the second builder will only run once for that injectable init annotation. It will take all those temporary generated files and make a single final file. From this approach, I'm going to take a wisdom of having two builders and temporary files that will then be merged in a single file. So we can finally start implementing our own solution. I have already prepared a package with annotations called Barrel Files Annotation. It's a tiny one that contains a single class and a const instance of that class. In Dart, any constant can be used as annotation, thus it's already enough. A barrel file for this package and a pubspec YAML file with no additional dependencies. That's all that is needed. Let's now implement the generator. I have already prepared some initial implementation, which I will walk you through and will improve it with additional features. So far, the implementation has a few dependencies. Analyzer and build are the basis for creating a code-generating package, and the sourceGAN we have already discussed. Basically, it contains a developer-friendly API wrapper over the build package. We also have our annotations among dependencies. Every code-generating package has to have a build YAML file that contains declarations for all its builders. Here is a declaration of my first builder. I called it individual barrel files. It is a builder that will walk through every individual file of the package, looking for our custom annotation. The declaration consists of a name of a function that will return a builder and an import where this function can be located. It also specifies that for each .dart file, the generated file extension will be .barrel. The build to cache indicates that those barrel files should not appear in the project and are temporary files that will save in cache. Very briefly, this is the file that we specified as an import. It is a barrel file for my package which exports two libraries in the source folder. And this is the individual barrel files builder function that we promised will return our builder. It uses a library builder from the sourceGAN package because we are going to generate files without part of directives. It repeats the promise to generate .barrel files, assuming the input consists of .dart files, and creates some individual barrel files generator. So let's check it next. This generator extends a generator for annotation generic class, and we pass our include and barrel file annotation type as type parameter. As a result, this generate for annotated element function will be called each time the runner meets a code element annotated with our include and barrel file annotation. This method accepts annotated element, which in our case can be a class, a global const, enum, type def, and anything else that can be a top library element. You can use it to get any information about the element like its name, list of fields and methods, and so on. It also accepts an annotation object, which you can use to read some properties of the annotation above the element. And finally, it accepts a builder step that gives us information about the input file and access to write to the output file if we wanted to. This method is expected to return a string. It can also return multiple strings in a stream or an iterable, and can also return a future of those types. It should return null in case we don't want any output for a given element. So what I do here is I take the name of the annotated element and send it in an array to the compose output method together with the build step input ID, which represents the input file. The compose output checks if the input array is not empty. And in current implementation, we see that it cannot be empty, but this soon will change. And it calls the compose export method that forms a valid Dart code with an export directive out of the input file URI and a list of names of the top elements it should expose. This is actually enough to be able to run our generator for the first time. Let's run the code generation with this command, dart run build runner build delete conflicting outputs. Let's check what was generated. Remember that we asked this builder to generate the code in cache, so we'll be looking for it in the .dart tool folder. Build, generated, example. Here is the output for the example1 file. At the top of the file, we see a standard header, the name of the generator that produced the code, and an export line for each element that was annotated. Let's check example2 file. Same situation here. We see there is no example3.barrel file because our example3.dart file input did not contain any annotated elements. And here is the last output. So far, so good. But let's check the example1 file again. We see that all these export directives contain the same URI and only the show element is different. I'd rather expect a single export directive with multiple shown elements separated by comma and sorted alphabetically. So let's do exactly that. I will now replace my implementation of individual barrel files generator with a new one. Because the generator for annotation base class is designed to have 0 or many outputs for every input in every input file, and I want to have 0 or 1 output for all inputs in the same file, I am going to change the base class and to implement my own generator. This time I have to override the generate function that accepts a library reader that allows me to parse the input Dart file and the build step we already saw previously. In this new implementation, I am reading a list of all top-level annotated elements from the library reader and collect all of their names in a list that is then sent to the composed output function. Now you know why it needed to check if the list is empty and then return null. This way, if the library contains no annotated elements, like the example3 file from the example package, no output will be generated for it. Let's rerun code generation. We now have a single export with a list of shown elements. Cool. Now let me show you a couple of improvements. The first one is related to the way the export directive is formed. I am adding two new dependencies, code builder and Dart style. Performing pub-get. Currently, the piece of Dart code to be placed in the output file is formed as a plain string. And there is nothing wrong with this approach, but I want to show you how you can generate more complex code and be sure you didn't make any syntactic error. Let me replace the compose output function implementation. In this version, I am using directive constructor to create an export directive, and I am creating a library object that will contain that directive. You can also create classes and other Dart language elements, add fields, methods, and so on. This API allows to provide more type-safe and error-prone Dart code. And then I also format the future code with Dart formatter. The output of the generator did not change, but I find this approach more mature. Next, I'd like to address a problem in my code. It always expects an element to have a name. But what if a user of my package has placed an annotation over the unnamed element, like this extension here? Let me rerun code generation to demonstrate what happens. we see that the generator failed with null check operator using a null value. That's not very informative message. Let's fix that. The error is caused by this exclamation mark I applied to the annotated element name. And clearly, due to the nature of my annotation and the approach I took to make individual code elements visible with show directive, my code requires for some name to be present, and annotating an unnamed extension leaves me no choice but to throw an exception. For these situations, the SourceGen package offers a special type of the exception, invalid generation source error, that may be thrown by generators during the generate method. So here I'm defining my own implementation of the invalid generation source error that defines an informative error message and passes an element causing the problem from constructor parameter to the base class. And here I'm throwing this unnamed generation source error if the annotated element name is null or empty. Let's now run the code generation again. I can now see a nice error message which clearly indicates where the problem is. Let me briefly remove the failing annotation. Okay, so far we looked into how a typical code generating package can be created with SourceGen, how to create a valid Dart code with Code Builder, and how to throw developer-friendly errors. Now it's time for the second builder. If you remember, we are supposed to end up with a single output barrel file, which will contain all of the temporary barrel files from the first builder. At the same time, so far we have only seen examples of situations where there definitely should be some kind of input Dart file, which then can be matched with the output file. And I don't want to cause any misunderstanding here. Even though the generator accepts a single input at a time, you are free to read any package resources and other files you need through the build step object. The point is that there should be some kind of input file to trigger the generate function. But in my case, I don't have any other file in the package that will serve as an input for my builder. I'm now back to the demo application from the Flutterby conference to show what I mean. For my package, I don't want to make users to create a single companion file like this one with the injectable init annotation from injectable, just because the code generation mechanism is built on this concept. So what can I do about it? Let's use some more inspiration from the existing solutions, specifically from the Flutter Gen Runner package. The idea of this package is to look through the list of all available package assets and generate a couple of output files with all the assets listed as generated class properties. Sounds similar to what I need, right? A builder that runs only once per package and which doesn't have any companion file that will be matched as its input. Let's see how they did it. Not going into many details, they are extending a builder class from the build package. And remember that previously we used a library builder from the SourceGen package, which is a soft wrapper over the builder API. Extending a builder requires overriding two methods, one of which is build extensions. The same build extensions that indicates the matching between input and output files in the build YAML file of the generator. But you see, this builder here has a special keyword $package$ as the returned map key. This will ensure this builder will only run once because the entire package will be considered its input. Okay, that's a great start. Let's define our own builder in a similar way. This one is called barrel files. It will be created with the barrel files builder function, and it will have the entire package as its input thanks to that package keyword. At this point, I cannot know the name of the output barrel file, so I'm just providing a dummy value there. It doesn't affect the end result. An important difference between this and previous builder is that this time the build_to value is set to source, which means our code will appear in the user package for real. And I also added one line to the previous builder that indicates that it should run before the second builder, as we want individual barrel files to be generated first before we go and collect all of them in a single final output. The builder factory is pretty straightforward. And here is my own builder implementation. So my package barrel files builder implements a builder and overrides two methods, build extensions and build. The build extensions method returns a map with the package key as we discussed. Now as to the map values, this is a place where we have to inform the build runner about the expected builder output, either the extension of the file or the full file name. Later on, if inside the generate function we try to write to a file that was not listed among the build extension's map values, we'll get an exception. Thus, this is a place to calculate and return the name of the future barrel file. Because build extensions method can be called multiple times, I decided to do that beforehand in the getBarrelFiles path function and cache it in the barrel file path field in the builder constructor. The final barrel file has to be located under the lib folder, and by default the file name has to match the name of the package. The challenge here is to get the package name without any additional input. Remember that this code is called when the builder is created, and there are no parameters that can help us understand where this is run. For the initial implementation of the getPackageName function here, I'm using the root package name getter from the source_gen package to detect it. But actually, this getter is not intended for public usage and is hidden under the source folder. So I have this warning here. That's why my next step should be to re-implement this function in my project using the same approach. Let's check how source_gen does it. They read a pubspec.yaml file synchronously and parse it with load_yaml function. I'll do something very similar in my package. So I add a YAML dependency and update the getPackageName method implementation to read the pubspec YAML file synchronously. Parse it to a map with the same load_yaml function and get the name property out of it. So that's how build extensions getter is implemented. I return a map with a special keyword that ensures the builder is run only once, and I calculate the future output file name in advance by reading the package name from the pubspec YAML file from the file system synchronously. Here I should point out that the build package documentation says that we should never touch the file system directly. At the same time, I don't see any other good way to achieve the result I wanted. Thus, I prefer to bend this rule for the sake of better developers' experience. However, this decision comes at a cost, and we'll see later how it made the final solution more complicated. Now it's time to implement the generate function of the builder. A reminder that we'll have to collect all the temporary generated files from cache and merge them in a single output file. So here is how it's done. First, I add the glob dependency that will help me to easily match all files with certain extension. And here is how the generate function is implemented. First, I find all files that have the .barrel extension using the build step find assets method, and read all of their content with build step read as string. This is an example of how actually you are not limited to reading only from the input file that was provided in the build extensions getter. Next, I cut off the headers of those temporary barrel files, as I want to have a single header in my result file. Here I form the final content of the barrel file, and finally I write to the output file with build step write as string. This build step allowed outputs array comes from the build extension's map values. Thus I know it has a single item that represents my barrel file name. So far that's it, and we can run code generation in our example project. Let's see. Here is a new generated barrel file under the lib folder called example.dart. And it's exactly the same as the expected example.dart file I created manually. Awesome! Now I want to demonstrate how users of code-generating packages can customize their behavior in the build YAML file. There is a number of built-in configurations supported by Build Runner out of the box, like Generate For, that allows users to limit the scope of the files that are looked through, or build extensions that allows to change the output file's path. And there is also a way to pass custom options to the builder so it can change its internal behavior. For my package, I want to allow users to change the output barrel file name. Here is the build YAML file with an example of the usage I intend to support. Users can customize my barrel files builder and pass an options map with the barrel file name key. To support that, first I will update this getBarrelFilePath method. It now accepts a map of options which can potentially contain that barrel file name key. And if it does, its value becomes a preferred name for the future barrel file. I also update the builder constructor to accept such a map and pass it to this method. And finally, I get this map from the options config parameter of the builder factory. Those options correspond to this options item in this build YAML file of the user package. So here I ask the generator to name the output file as customexample.dart. I can now rerun code generation, and we see that previously generated example.dart file has disappeared, and instead we have a new customexample.dart file with the same content. So, to recap, we have just created a second builder where we used the plain builder as the base class. We saw how to make it run only once per package. We also learned how to quickly find all files that match certain pattern and how to read and write file content using build step object. And finally, we saw how to implement builder behavior customization using builder options. Now I want to talk to you about testing. I'm sure you don't want to only rely on reviewing the generated files manually every time you make a change in the generator logic. So, in general, if you have implemented your builder with one of those builders from the SourceGAN package and have used generator for annotation as the base class for the generator, then SourceGAN test is a package that can help you test your generators easily. All that's needed is to create an example usage of the annotation like the test annotation here, and provide should generate or should throw depending on what you expect. The full example can be found in the SourceGAN repository. But in my case, even though for my first builder I have used a library builder from SourceGAN, I inherited my generator from the plain generator class. And for the second builder, I have directly implemented a builder from the build package. Thus, for testing both of my builders, I have to use the build test package. It provides a useful test builder function that accepts input files and expected output files and compares the actual output with the expectations. Let's use it for my tests. First, I add test and build test dependencies. Let's start with the testing individual barrel files generator. Here is an example of a test. This one will create a couple of .dart files. Each will contain a single annotated element. And it will test that for each such input file, there had been created a corresponding .barrel output file with a single export directive and a single shown element. This is the file name of the first input file, test1.dart file under the lib folder, and this is its content, an example class annotated with include_barrel file annotation. And this is the output that this input is expected to produce, the test1.barrel file under the lib folder. Here is the test package name and header values. So it's expected that a test1.barrel file will contain a default header and one export directive. Here is another pair of inputs and expected outputs. So next I create a builder by calling the same factory function that is declared in the build YAML file and call a test builder function. It accepts my builder, the map of file names and contents which represents a builder input, and then a similar map with expected outputs. Let's run this test. Uh-oh, it didn't pass. Let's see what the problem is. Could not resolve the annotation for class example class. The problem is that in the mock test package where the builder is executed with this test builder function, there is no such dependency as barrel files annotation. It is a dependency of this barrel files generator package where we run these tests. So what we can do is to tell test builder function to run builder as if it is used in this very own package. We can do that by providing a reader that can resolve files known to the current isolate. Let's run the test again. Now it passes. So we just looked into how to write tests for builders with test builder function from the build package and how to fix the problem in case there is a separate annotations package involved. Clearly, this builder here requires more tests to be fully covered, but they will all be similar to this one. So I'll move on to testing the second builder. .barrel files that were the output for the first builder are the inputs for this package builder. So here I declare a couple of input.barrel files in a similar manner. This is their header, and the test package name is the same. I expect to have a single output file from this builder. It should be named after the test package. It should contain a single header and all export directives from all input files. The rest is the same. I create a builder by calling the factory function and use the test builder function. No reader is needed for this test, as we no longer are at the risk of unknown annotations. Let's run this test. It also fails. Let's see. We expected to have a test package Dart file to be created, but instead a barrel file .dart file was created. How is that? Well, remember how we detect the name of the package? We load the pubspec YAML file from the file system and read its name property. That's exactly what this builder did. It found a pubspec YAML file of this barrel files package and read its name, barrel files. This is the cost of using the real file system in the places where you were not supposed to. So, how to resolve this situation? Let's go back to our source of inspiration and check one more code-generating package. This time it is BDD widget test. They also have a similar challenge because the generator is reading from the file system directly. So they have a file system global getter, which by default returns an instance of the local file system. It is a wrapper implementation around Dart.io. So basically it's the real file system. And they implemented an ability to provide a mock instance of a file system from tests. Let's do something similar. First, I add the file dependency. Then I add an optional file system parameter to the builder factory and pass it to the builder. Now inside the builder, I accept it as a parameter and pass it to the getBarrelFile pass function. And finally, it gets delivered to the getPackageName function, because that's where we read the pubspec file. Now here, instead of creating a file object, I initialize a file system variable which either equals to the file system object passed a parameter or the local file system, and read the pubspec YAML file from it. Finally, I can update tests. Here I create a memory file system, which is an in-memory implementation that is easy to configure with mock files. Here I write to the mock pubspec.yaml file, and this is what's in that file. As we see, it provides the expected test package name to the name property. What's left is to use this memory file system object as a parameter to the builder. And run the test. Now it passes. So we just saw another example of testing builders with test builder function and how to work around the side effects of using the file system to read package assets. This wraps up the topic of creating a code-generating package for me. We saw various approaches and tools developers can use when solving this task. and even broke some rules for a better user experience. But what's more important, I hope I managed to demystify the task of creating a code-generating package by showing how you can explore existing solutions and get answers to most of the challenges you can face. The barrel files package we were developing today is already published on pub.dev, and all of its source code is open on my GitHub. So go check it out, give it a thumbs up, and a star if you like it. Automating even such a small thing as maintenance of barrel files can save developers some time in the long run. So I hope this talk was useful and inspirational, and there will be even more code-generating packages available to automate various daily developers' tasks. Thanks for watching!